Yeah.
If you took a time machine back about 2.4 billion years and just stepped outside, you would be dead before you even realized what was happening.
Oh, absolutely. Instantly.
Yeah, the sky above you wouldn't be blue. It would be
Yeah.
this hazy, suffocating, like pale orange or even a smoggy red color.
Right.
And if you looked out at the oceans, you wouldn't see deep, vibrant blue water.
Yeah.
You'd be staring at this murky, toxic expanse of deep green or red that was just absolutely saturated with dissolved iron.
It's basically an entirely alien world compared to what we know today.
Completely alien. And if you tried to take a deep breath, your lungs would pull in this mixture of nitrogen, carbon dioxide, and methane. There was virtually zero free molecular oxygen.
None at all.
Right. And to the single-celled archaea and early bacteria that were dominating the planet at that time, oxygen was a highly corrosive, deadly poison.
It was toxic to them. But today, we're going to look at how a microscopic bacteria in those toxic oceans essentially exhaled the future of our entire planet.
Yeah.
And more importantly, how the chemical footprint of that single event is literally powering the most advanced technologies we have today.
Exactly. We have an incredibly fascinating mission for this deep dive. We are exploring how a very specific, highly exclusive set of rare and highly reactive elements acts as this sort of chemical diary of Earth's ancient history.
A diary that also serves as the literal physical building blocks of our clean energy future.
Right. Looking through the stack of sources we have today, which includes this massive MDPI scientific review on advanced techniques for thorium recovery and extensive Department of Energy documentation covering the Great Oxidation Event, the Cerium anomaly, and rare earth elements, we're basically tracing a direct line from 2.4 billion years ago directly into the electric vehicles and nuclear reactors of tomorrow.
It's quite the journey.
Okay, let's unpack this.
So the crucial starting point here is understanding that the oxygen we rely on didn't just passively appear, it was manufactured.
Right.
And it triggered the most catastrophic and transformative event in the history of the Earth, which is known as the Great Oxidation Event, or the GOE, which occurred in the Paleoproterozoic era.
And the sources outline this massive biological shift that kicked all of this off. A specific type of microorganism, cyanobacteria, evolved a completely new trick.
Yeah, they figured out how to harness the energy of the sun.
To perform oxygenic photosynthesis, they started pulling in water and carbon dioxide, using sunlight to build their cellular structures, and releasing molecular oxygen as a waste product.
But what's really fascinating here is the timeline. The geological record indicates that these cyanobacteria actually evolved the ability to photosynthesize hundreds of millions of years before the atmosphere started filling up with oxygen.
Wait, really?
Yeah, we're looking at a delay of at least 400 million years.
That seems entirely counterintuitive. I mean, if these bacteria are multiplying across the globe and constantly pumping out oxygen, why did it take nearly 500 million years for the air to actually become breathable? Like, where was all that oxygen going?
It was being instantly consumed by what geochemists call oxygen sinks.
Okay.
You have to remember how highly reactive oxygen is. It desperately wants to bond with other elements to achieve a stable electron configuration. And the early Earth was absolutely covered in raw, unoxidized materials just waiting to react.
Oh, I see where this is going. The early Earth is essentially a giant chemical sponge.
That's a great way to think about it.
If you have a massive bone-dry sponge on a tile floor and you turn on a dripping faucet right above it, the water won't start pooling on the floor until that entire sponge is completely saturated.
Exactly. The cyanobacteria are the faucet, just dripping oxygen. But early Earth didn't just have one sponge, it had three massive ones.
Why were they?
First, the oceans were full of dissolved ferrous iron. As soon as a cyanobacterium released a molecule of oxygen, it would react with that dissolved iron, instantly creating insoluble ferric iron.
So it literally turned to rust.
Yeah, it turned to rust and sank to the ocean floor. Second, the atmosphere was thick with methane produced by other microbes which reacted with the oxygen. And third, the intense volcanic activity of the early Earth was constantly spewing out reduced minerals and gases that eagerly bonded with any free oxygen.
So the oxygen was basically losing a war of attrition.
Completely.
It was being destroyed the second it was created. But obviously we're breathing today, so the faucet eventually beat the sponge. What caused the tipping point?
The Department of Energy documents highlight a really compelling mechanism for this, known as the nickel famine.
The nickel famine.
Yeah. Early in its history, the Earth's mantle was significantly hotter. This led to the eruption of these ultramafic lavas called cometidates, which churned massive amounts of nickel into the oceans.
And nickel is relevant here because it's a vital nutrient for methanogens.
Precisely. Methanogens use nickel-dependent enzymes to produce methane. So a hot Earth meant lots of volcanic nickel, which meant methanogens were thriving, just pumping immense volumes of methane into the atmosphere.
And that methane was a voracious oxygen sink.
Right, it was gobbling up the oxygen before it could accumulate.
But the Earth is a cooling system, right? Over hundreds of millions of years, the mantle cooled down.
And as it cooled, the nature of volcanic eruptions shifted. Those cometite lavas stopped forming, and the amount of nickel flowing into the oceans plummeted to a fraction of its former levels.
Wow.
So without that nickel pipeline, the methanogens were starved of the cofactors they needed for their enzymes. They suffered a global famine.
So as the methanogens died off, methane production crashed. Suddenly, one of the biggest oxygen sinks was just gone.
Exactly. The cyanobacteria were still pumping out oxygen, but the main chemical defense mechanism against it had collapsed. The balance finally tipped.
So the dissolved iron in the oceans eventually all rusted out, the methane was depleted, and finally, the oxygen had nowhere else to go but up into the atmosphere.
That's the sequence of events, yeah?
Hold on, though. I need to stop you there. You're losing me a bit on the certainty of all this. I mean, we're talking about microscopic bacteria, invisible gases, and global ocean chemistry from over 2 billion years ago. The geological record from that far back has mostly been subducted into the mantle or melted down.
Right, it's very sparse.
So how do we actually know this timeline isn't just a massive, highly educated guess? How do we prove the sponge was full?
That is the exact skepticism scientists apply, and it's why we rely on hard geochemical evidence that is practically irrefutable.
Okay, lay it on me.
The most persuasive piece of evidence we have is the mass-independent fractionation of sulfur, or MIF.
How does a rock's sulfur content tell us if there was an atmosphere?
Well, to understand this, we have to look at how chemical reactions usually handle isotopes.
Right.
Isotopes are just versions of an element with slightly different weights, different numbers of neutrons. Normally, chemical reactions separate isotopes based on their mass. Heavier isotopes vibrate a bit slower and form slightly stronger bonds. Lighter ones move faster.
Okay, that makes sense. Mass-dependent fractionation.
Exactly. But sulfur found in rocks older than 2.4 billion years shows a bizarre, chaotic pattern that does not depend on mass at all.
What could cause a chemical reaction to ignore the mass of the atom? That breaks the rules, doesn't it?
Deep UV photolysis. The only way this specific mass-independent signature can be created in sulfur is if sulfur dioxide gas in the atmosphere is being blasted by raw, unfiltered ultraviolet radiation from the sun.
Whoa.
The high-energy UV light breaks the molecules apart in a quantum process that completely ignores the mass differences of the isotopes. Those altered sulfur isotopes then rained down and were locked into the sedimentary rock.
But wait, unfiltered UV radiation shouldn't be reaching the lower atmosphere? We have the ozone layer to block that?
And what is ozone?
It's O3, 3 oxygen atoms.
Right. If there is no free oxygen in the atmosphere, there is no ozone layer. The presence of this specific, chaotic sulfur signature in the rocks proves that the early Earth had no ozone sunscreen. But right around 2.4 billion years ago, that MIF sulfur signature abruptly and completely disappears from the geological record across the entire planet.
That is brilliant detective work. The cyanobacteria finally filled the atmosphere with enough oxygen to create the ozone layer.
Yep.
It acted as a global shield, blocking the UV light, which instantly stopped that specific sulfur reaction. So the sudden absence of a chemical reaction is the definitive proof of the atmosphere changing.
Exactly. And we also have massive visual evidence in the form of banded iron formations, or BIFs.
Right, the ocean rust.
Yeah, when that dissolved iron in the ocean met the oxygen and turned to rust, it precipitated out. It rained down on the ocean floor for millions of years, creating massive layers of alternating iron oxide and silica.
Wow.
Most of the commercial iron ore that humanity mines today comes from these specific formations. They peak right around the time of the GOE, giving us a literal physical timestamp of the ocean's oxygenating.
The sources also mention something called the degree of pyritization, or DOP. This is used to measure how anoxic an environment was.
Right, DOP is a ratio. It measures how much iron is bound up in pyrite, which is iron sulfide, or fool's gold, compared to the total highly reactive iron in a sample.
Yeah.
Pyrite only forms under highly reducing, sulfur-rich conditions where oxygen is completely absent, what we call eusinic conditions. If a sedimentary rock has a DOP near one, it means almost all the reactive iron turned into pyrite, proving the deep water was completely devoid of oxygen when that mud settled.
Got it.
Tracking DOP changes lets us map the exact progression of oxygen infiltrating the deep oceans.
So we have the UV blocking sulfur evidence, the global layers of ocean rust, and the fool's gold ratios. The evidence is incredibly solid. But introducing a highly reactive element into an unoxidized world must have had apocalyptic consequences.
Oh, for the anaerobic life that existed, it was the first mass extinction. Oxygen was a toxic electron-stealing menace to their cellular machinery.
And it changed the climate too, right?
It triggered a massive climate catastrophe. Because methane is a powerful greenhouse gas, it was keeping the early Earth warm despite the sun being significantly dimmer back then.
So when the oxygen surged and wiped out the atmospheric methane,
Earth lost its thermal blanket.
that plunged the planet into the Huronian glaciation. The Earth essentially became a giant snowball for millions of years.
It did. But, from a geological perspective, the introduction of oxygen caused an explosion of mineral diversification. Before the GOE, the Earth had a relatively boring, limited mineral portfolio.
Right, because things weren't reacting.
Exactly. When oxygen hit the surface, it began reacting with everything. It's estimated that the GOE was directly responsible for creating over 2,500 new oxidized and hydrated minerals.
It also forced an incredible biological adaptation, right? The toxic oxygen environment created intense selective pressure.
Absolutely. The leading theory is that certain archaea, trying to survive, actually engulfed another bacterium that had evolved the ability to handle and use oxygen for energy production.
And that engulfed bacterium became the mitochondria.
Yes. That symbiosis led to the origin of eukaryotes' complex cells with the nucleus and specialized organelles. Every plant, every animal, and every human being is the direct result of life finding a biochemical workaround to survive the Great Oxidation Event.
That's wild. So if the Great Oxidation Event rusted the entire ocean and forced the creation of thousands of new minerals, that chemical footprint must still be trapped in the rocks. How do modern geologists actually find the chemical footprint of a 2.4 billion-year-old breath of oxygen?
They look for elements that function as chemical timestamps. Elements whose physical behavior changes drastically depending on whether oxygen is in the room. And that brings us to the cerium anomaly.
Cerium. Let's dig into this. What makes cerium so uniquely qualified to track oxygen?
Cerium is part of a group called the lanthanides. Now, the defining characteristic of almost all lanthanides is that they only exist in one stable oxidation state, which is +3. This means they've lost 3 electrons.
Okay, they're +3.
But cerium has a unique electron configuration. It can exist as cerium-3, or if conditions are right, it can lose a 4th electron and become cerium-4.
And the trigger for losing that 4th electron is oxygen.
Exactly. Under reducing conditions, when oxygen is scarce, cerium stays as C3+. In this state, it's soluble and behaves just like all the other rare earth elements. It stays dissolved in magmas and hydrothermal fluids.
But when the environment becomes oxidizing,
When there's free oxygen available to pull that extra electron away, it becomes C4+. And the moment it oxidizes to C4+, it becomes highly insoluble. It precipitates out as cerium oxide and drops completely out of the fluid solution.
so it's literally a molecular rust detector. If it stays dissolved, the environment was oxygen-starved. If it drops out as a solid, oxygen was present. How do geologists actually read that in a rock today?
They look for anomalies in highly resilient crystals, particularly zircons. Zircons are incredibly tough. They can survive intense heat, pressure, and weathering, making them perfect time capsules. When a felsic igneous rock is forming from magma, zircon crystals start to grow out of the melt. Now, the chemical formula for zircon is zirconium silicate. Zirconium has a +4 charge.
And cerium-4 also has a +4 charge.
Yes. Not only do they share the exact same charge, but their ionic radius, their physical size at the atomic level, is incredibly similar. Cerium-4 has a radius of 0.97 angstroms, and zirconium is 0.84 angstroms.
So from the perspective of the growing crystal lattice, they look practically identical. The crystal is looking for a +4 block of a specific size to build its structure, and cerium-4 fits the slide perfectly.
Exactly. If the magma is oxidized, cerium turns into cerium-4, mimics zirconium, and gets locked away inside the indestructible zircon crystal.
Oh,
We call this a positive cerium anomaly because when we analyze that zircon today, we see a massive spike in cerium compared to the other rare earth elements that were left behind in the magma.
But if there was no oxygen in the magma?
Then the cerium stays as cerium-3. It only has a +3 charge, its physical size is slightly different, and the zircon crystal lattice rejects it.
It's like a bouncer at a club checking IDs. If you don't have the +4 charge, you're not getting into the zircon crystal.
That's a perfect analogy. The zircon grows without the cerium, resulting in a negative cerium anomaly. By measuring these specific anomalies in zircons of different ages, we can map the exact oxidation state of magmas and the surrounding crust over billions of years.
The sources provide a really interesting contrast to illustrate this in the real world.
Yeah.
Looking at coal deposits. Coal usually has a weakly negative cerium anomaly.
Right.
This makes sense because coal forms in swampy, reducing oxygen-poor environments. The sources say this is especially true for coal mined in regions dominated by felsic rock, like the Guangzhou coalfield in China.
Right. During the weathering of the surrounding felsic rocks over millions of years, the environment is highly oxidized. Cerium oxidizes to C4+, precipitates out as a solid oxide, and gets left behind in the local soils.
Oh, I see.
Because it drops out of solution early, very little of it washes into the swamp basins that eventually compress into coal. Thus, the coal is depleted in cerium.
But the data shows massive exceptions that prove the rule. In places like the Pavlovka deposit in Far East Russia, they find enormous positive cerium anomalies in the iron-manganese ores associated with the coal. Why there?
That occurs because volcanic ash erupted over the area and weathered into mafic tuffs. Manganese oxides are incredibly efficient scavengers of cerium-4.
So they just soak it up.
Exactly. When the localized environment oxidized, the cerium flipped to a +4 state and got absorbed directly onto the surfaces of those manganese oxides, creating a massive, highly localized spike in the geological record. Its physical location is entirely dictated by the presence or absence of oxygen.
It's just such an elegant tracking mechanism. But cerium is just one member of a highly exclusive chemical club, the rare earth elements.
Oh, yes.
While cerium helps us read the deep geological past, its siblings are literally powering the present.
The rare earth elements, or REEs, are arguably the most critical materials in the modern global economy. There are 17 of them. You have the 15 lanthanides, which occupy that floating row at the very bottom of the periodic table, elements 57 through 71 plus 2 transition metals that act chemically similar, scandium and yttrium.
Let's address the name right off the bat because rare earth is a massive misnomer.
It is entirely misleading. They are not actually rare in terms of sheer volume in the Earth's crust. Cerium, for instance, is more abundant than copper.
Really? More abundant than copper?
Yes. Neodymium is more common than cobalt. Even the rarest of the rare earths are significantly more abundant than gold or platinum.
If they aren't rare, why the intense geopolitical scramble for them? Why are they so difficult to source?
Because they are heavily dispersed, they are lithophile elements, meaning they love to bond with oxygen and silica, but because of their large ionic radii, they don't easily fit into the crystal lattices of common rock-forming minerals.
So they kind of get squeezed out.
Exactly. As magma cools, they get squeezed out and end up scattered relatively evenly throughout the crust in very low concentrations. Finding a concentrated ore deposit like a vein where they are packed densely enough to be economically viable to mine is incredibly rare.
Okay, so the physical dispersion is a nightmare for mining. But why are we so desperate to find them? What makes them the absolute backbone of clean energy, military tech, and consumer electronics?
To understand that, we have to look at the bizarre physics of their electrons, specifically the orbital.
This is where things get heavily into quantum mechanics. How does the orbital make these elements behave differently than, say, iron or copper?
Well, if you think of an atom's nucleus as a magnet, the electron shells are like layers of bubble wrap surrounding it.
Okay, bubble wrap.
For most transition metals like iron or copper, their outermost electrons, the ones interacting with the world and forming chemical bonds, are right on the surface. But for the lanthanides, their active electrons are in the 4 subshell.
And the 4 subshell is buried deep inside the atom.
Yes. The fel electrons are shielded by completely full outer shells of electrons. So the active electrons are physically hidden behind a layer of spherical bubble wrap.
That's a great visual.
This creates 2 massive consequences. First, because their outermost layers are identical, they all have nearly identical chemical properties. They behave identically in nature, which is why they all lump together in the exact same rocks.
Right.
Second, because those pholectrons are shielded from outside chemical interference, they retain incredibly unique, undisturbed magnetic and optical properties.
Let's focus on 3 or 4 of the most critical ones to see how that inner orbital translates to modern technology. Let's start with the heavy hitters: neodymium, praseodymium, and dysprosium.
These are the magnet kings. Neodymium has 4 unpaired electrons buried in its orbital. Because they are shielded, their magnetic spins can align perfectly without being disrupted by adjacent atoms.
Wow.
When you alloy neodymium with iron and boron, you create a crystalline structure that locks those electron spins in place, creating the strongest permanent magnets on Earth.
And these magnets are the absolute core of electric vehicle motors and the generators inside wind turbines, right? You need a massive magnetic field to generate electricity from the rotation of a turbine blade, and you need it to be lightweight. Without these rare earths, the generators would have to be incredibly massive and inefficient.
Exactly. And dysprosium is specifically added to the alloy because it increases the magnet's coercivity.
Coercivity, meaning its resistance to losing its magnetism at high temperatures.
Exactly. An EV motor gets incredibly hot. Without dysprosium, the neodymium magnet would just demagnetize on the highway.
That would be bad. What about the optical properties? The sources mention erbium as being vital for global communications.
Erbium is a perfect example of how that shielded orbital works for optics. When you pump energy into an erbium atom, its shielded electrons get excited and jump to a higher energy state. When they drop back down, they release a photon.
Okay.
Because they're shielded from outside chemical noise, the photon they release is an incredibly precise wavelength.
Okay.
Exactly 50 nanometers.
Which happens to be the exact wavelength of infrared light that travels with the absolute lowest loss through silica glass optical fiber.
Exactly. So we dope the transatlantic fiber optic cables with erbium. When a weak data signal traveling across the ocean hits the erbium, lasers pump energy into the atoms, the erbium releases identical 50 nanometer photons, and the signal is amplified purely optically without ever having to be converted back into an electrical signal.
That's insane. The modern internet literally relies on the quantum quarks of erbium.
It really does. We also see gadolinium used in medicine. Because it has 7 unpaired electrons, it has a massive magnetic moment. When injected into the body, it alters the magnetic relaxation times of nearby water molecules, which is what allows soft tissues to light up brilliantly on an MRI scan.
And terbium and europium provide the precise green and red phosphors for our LED displays. Every screen relies on the precise wavelengths emitted by these shielded electrons.
Yep, every screen you look at.
Okay, so if these elements are the secret sauce of the 21st century, if we need millions of tons of neodymium for wind turbines to hit our climate goals, how do we actually gather them? This brings us to the massive paradox of the rare earth supply chain.
Right, the paradox.
If I want to mine iron, I find a concentrated deposit of iron oxide, dig it up, throw it in a blast furnace with some carbon to strip the oxygen, and I pour out liquid iron. Why can't we just mine rare earths like that?
The smelting process you just described works because iron's chemical bonds can be easily broken with heat and carbon. Rare earth mining is an entirely different beast.
How so?
First, because of that identical outer electron shell we talked about, you never find a rock of pure neodymium. You find a complex mineral like monazite or bastnasite that contains all 15 lanthanides densely mixed together in a stubborn phosphate or silicate matrix. You have to strip mine massive amounts of raw ore just to get a tiny fraction of the mixed elements.
So you're digging up tons of dirt for incredibly low yields. But separating them from the rock and then from each other is where the real bottleneck lies.
It is arguably one of the most complex, chemically brutal, and energy-intensive processes in modern industry. You have to crush the ore into a microscopic powder. Then, to break that phosphate matrix, you have to roast it in concentrated acids, usually sulfuric or hydrochloric acid, at hundreds of degrees.
Basically boiling rock in acid.
Exactly. This creates a highly acidic, toxic liquid soup containing all the rare earths.
They're still mixed together in the liquid.
Right. And because they behave identically, you can't just use a simple chemical reaction to precipitate one out. You have to use a process called solvent extraction.
Which is what exactly?
You mix the water with organic solvents that have a microscopic preference for one element over the other based on minute differences in their atomic radius. To separate neodymium from praseodymium, you have to run the liquid through hundreds of sequential extraction stages, gently nudging the elements apart over weeks of processing.
The environmental cost detailed in the sources is staggering. I mean, you have the habitat destruction from massive open pit mines. You have the intense energy required to maintain hundreds of degrees of heat and run thousands of mixer settler tanks. And worst of all, you have the toxic waste.
It's a huge issue.
You are cycling vast quantities of violent acids, and the leftover liquid, the raffinate, is highly toxic, loaded with heavy metals, and frequently radioactive.
Which perfectly explains the geopolitical vulnerability here. The environmental regulations for managing this kind of toxic radioactive processing are incredibly strict in the West.
Right.
The capital cost to build a facility that complies with those regulations are astronomical. Consequently, a very small number of nations, primarily China, have cornered the market on processing and refining REEs. They endure the localized environmental devastation to control the global strategic resource.
Wow.
If you want to build an EV in the US or Europe, your supply chain is tethered to that singular, heavily concentrated processing node.
But looking through the Department of Energy documents, there is a fascinating pivot happening. The DOE is actively researching how to bypass traditional mining entirely and extract rare earths from secondary sources. Specifically, they're looking at coal and coal byproducts.
This is a brilliant shift in resource management. For over a century, industrialized nations have been mining and burning coal for power. This process left behind literal mountains of coal ash and vast networks of acid mine drainage. What geochemists have realized is that coal ash contains surprisingly high concentrated levels of rare earth elements.
Well, it makes sense. When you burn the carbon away, whatever heavy metals were in the coal get concentrated in the remaining ash. And the best part is, we already dug up the rock, we already crushed it.
Exactly. The environmental damage of the actual mining phase occurred decades ago. The DOE's angle is that if we can scale the hydrometallurgical technologies to extract the light and heavy rare earths from this existing coal ash, we hit a trifecta.
What's the trifecta?
First, we establish a secure domestic supply chain of critical minerals that is insulated from geopolitical choke points. Second, we drastically mitigate the environmental impacts of opening brand new rare earth open pit mines. And third, we are incentivizing the cleanup of toxic fossil fuel waste.
We're literally mining the garbage of the 20th century to build the clean energy infrastructure of the 21st.
It's an incredible opportunity.
But whether we are processing coal ash or raw monazite ore, there is a ghost in the machine. A highly reactive radioactive hitchhiker hidden in the exact same rocks. And here's where it gets really interesting, because this massive headache of a byproduct might just be the holy grail of nuclear energy.
We're talking about thorium.
Thorium, element 90 on the periodic table.
Right, it's a naturally occurring, slightly radioactive actinide metal. Geochemically, it loves the exact same environments as rare earth elements. It is heavily concentrated in phosphate and silicate minerals. The major commercial source is monazite, which is a rare earth phosphate that can contain anywhere from 4% to 12% thorium dioxide.
So the irony here is that when a country mines monazite to get neodymium for wind turbines, they inevitably end up with thousands of tons of thorium tailings as a direct waste product.
Yes. Historically, the industry has viewed thorium entirely as a liability. It's radioactive waste that requires expensive, highly regulated storage and monitoring while you extract the rare earth you actually want to sell. But nuclear physicists look at those exact same tailings and see an absolute goldmine.
The MDPI review explicitly pitches thorium as a superior alternative to uranium for nuclear power. Let's walk through the exact physics of why it's better, because there are 4 massive advantages.
Let's do it. The first is pure abundance. Thorium is approximately 3 to 4 times more abundant in the Earth's crust than uranium. We are not at risk of running out of it, especially considering we're already pulling it out of the ground as a byproduct of rare earth mining.
Okay, the second advantage is the breeding cycle.
Yeah.
And this requires a bit of nuclear physics to understand. How does a thorium reactor actually generate power compared to a uranium reactor?
Well, the current global nuclear fleet runs on uranium. Natural uranium pulled from the ground is over 99% uranium-238, which is relatively stable, and less than 1% uranium-235, which is fissile.
Fissile meaning it readily splits and causes a chain reaction.
Right. To make a traditional reactor work, you have to take that raw uranium and put it through a dizzyingly expensive, highly complex process called enrichment to artificially increase the concentration of U-235.
Which is a huge bottleneck.
And this enrichment process is also the exact same technology used to build nuclear weapons, which creates massive proliferation risks.
But thorium operates entirely differently. Natural thorium is almost 100% thorium-232.
And thorium-232 is fertile, not fissile. If you hit it with a neutron, it doesn't split. It absorbs the neutron. When it absorbs the neutron, it becomes thorium-233, which is unstable. It quickly undergoes two beta decays, meaning it spits out an electron to turn a neutron into a proton and transforms into uranium-233.
And uranium-233 is highly fissile.
Exactly. The uranium-233 splits beautifully, releasing immense thermal energy and spitting out 2 or 3 more neutrons, which then hit the next batch of thorium-232, continuing the cycle.
Oh, I see. It is like having a wood stove that automatically chops its own firewood as it burns.
I like that.
You feed it inert, non-weaponizable thorium, and it breeds its own highly efficient fissile fuel right there inside the reactor core. You completely bypass the need for massive, expensive enrichment facilities.
That analogy is perfectly apt. And the third massive advantage is what comes out of that wood stove. Managing nuclear waste is the primary public objection to nuclear power.
Definitely.
When traditional uranium fuel is burned, the U-238 atoms often absorb neutrons without splitting. They become heavier and heavier, moving up the periodic table to create what we call transuranic elements like plutonium, americium, and curium.
And those are the incredibly nasty, highly radioactive, long-lived wastes that have to be buried in deep geological repositories like Yucca Mountain for tens of thousands of years.
But thorium starts much lighter. Its atomic mass is 232 compared to uranium's 238. For a thorium atom to turn into plutonium-239, it would have to absorb a ridiculous number of neutrons sequentially without ever splitting in the process.
Oh, so it just probabilistically won't happen.
The physics are heavily stacked against it. As a result, a thorium fuel cycle generates a tiny fraction of the long-lived transuranic waste. The waste it does produce is dominated by fission products that decay to safe background radiation levels in a few hundred years, rather than tens of thousands of years.
That is a massive difference. The fourth advantage the sources point out is thermal stability. Thorium dioxide has the highest melting point of any known oxide, around 3,300 degrees Celsius.
It's incredibly stable.
It provides a much more stable heat dissipation capacity. Especially when used in advanced designs like molten salt reactors, it operates safely at much higher temperatures and is incredibly stable during reactor anomalies. The inherent risk of a catastrophic core meltdown is drastically reduced.
Yes, the safety profile is completely different.
Okay, let's follow that logic. We have a fuel that is 3 times more abundant, doesn't require weapons-grade enrichment, produces significantly less toxic waste, and is fundamentally safer from meltdowns, which naturally leads any sane listener to ask, why aren't our cities powered by thorium right now?
Because getting it out of the rock is a chemical nightmare. We discussed how difficult it is to separate rare earths from the phosphate matrix of monazite. Thorium is locked inside that exact same impenetrable titanium safe of a mineral.
So let's deep dive into the thorium bottleneck, breaking the mineral matrix. Our MDPI review goes into excruciating detail on the physical and hydrometallurgical extraction of thorium. It's a multi-stage battle against chemistry.
It really is. It starts with physical enrichment. Before you use expensive, dangerous chemicals, you use physics to concentrate the ore. When you crush monazite sand, you have a mix of the heavy rare earth and thorium minerals and lighter, useless ballast minerals like quartz and feldspar.
Right.
Because monazite has a high specific gravity, the first step is gravity separation. They literally use giant spiral sediment separators that use water and centrifugal force to spin the heavy monazite particles outward, separating them from the lighter sand.
You use magnetic separation.
Yes. Because of the rare earths inside it, monazite is weakly magnetic. So you pass the concentrated sand through a high-gradient magnetic separation system, or HGMS. Powerful electromagnets pull the monazite away from the non-magnetic minerals. You can also use electrostatic separation, bouncing the particles over high-voltage drums to separate them based on their electrical conductivity.
You're sorting millions of tons of sand, grain by grain, using gravity, magnets, and static electricity.
It's wild to think about.
But once you have the highly concentrated monazite, you hit the chemical wall. You have to dissolve the rock to get the thorium out.
And the rock absolutely refuses to dissolve. This brings us to chemical leaching. The traditional brute force method is acid leaching. The most common agent used is highly concentrated sulfuric acid, H2SO4. But as we discussed earlier, you can't just pour it over the rock at room temperature.
You have to aggressively bake the ore.
Yeah. You mix the concentrated sand with the sulfuric acid and roast it at extreme temperatures, anywhere from 200 to 800 degrees Celsius for hours.
What exactly is happening molecularly when you do that?
The extreme heat and the highly corrosive acid work together to literally break the covalent bonds of the phosphate matrix. It transforms the solid mineral into soluble metal sulfates. Under these extreme conditions, you can achieve 85 to 95% efficiency in dissolving the thorium.
So if we're basically melting rock with acid, do we just pour the absolute strongest acid we have on it? What about hydrochloric or nitric acid?
Hydrochloric acid, HCl, does work, but only if it's highly concentrated, achieving about 90 to 95% efficiency. But interestingly, the chemical structure of monazite is remarkably resistant to nitric acid.
Really?
The sources point out that even at high concentrations and high temperatures, HNO3 gets under 10% recovery. It practically bounces off the mineral structure.
But the massive downside to acid baking is the collateral damage. Sulfuric acid doesn't just dissolve the thorium. It dissolves the rare earths, the iron, the residual uranium, creating this incredibly complex, highly acidic, highly toxic soup that is immensely difficult to purify later.
Exactly, which is why the alternative alkaline leaching is becoming so crucial. Instead of violent acids, you use highly concentrated lye sodium hydroxide, NaOH. You place the ore in an autoclave, essentially a giant industrial pressure cooker, and blast it with 130 to 180 degrees Celsius lye.
Wait, I noticed a massive paradox in the data here.
What's that?
The sources explicitly state that alkaline leaching leaves the thorium as an insoluble hydroxide. It literally stays as a solid chunk in the bottom of the vat. Why on earth would we spend massive amounts of energy and caustic chemicals on a process that doesn't even dissolve the thing we're trying to extract?
It sounds completely counterintuitive, I know, but it is actually a highly elegant preparatory strategy. Think of the monazite crystal as a highly secure titanium safe, and the thorium is the gold locked inside. Sulfuric acid is like trying to open the safe by blowing it up with dynamite. It works, but it destroys everything inside and creates a massive, tangled mess.
So what is the alkaline lye doing?
Well, sodium hydroxide doesn't dissolve the thorium, but it perfectly targets and melts the walls of the safe. It attacks the phosphate and silicate matrix itself. The reaction turns the solid phosphorus into soluble sodium phosphates, which dissolve perfectly into the liquid lye. You can then simply drain that liquid away.
Leaving the thorium exposed.
Precisely. You have melted the safe and washed it away. What is left behind is a solid pile of exposed thorium and rare earth hydroxides. Now, because the protective matrix is gone, you can come in with a very mild, targeted acid wash. The thorium dissolves easily into the weak acid without needing to be roasted at 800 degrees.
That's brilliant.
It requires 2 distinct steps, but it yields a much cleaner, higher purity solution and avoids the massive collateral damage of straight acid baking.
Okay, so whether we blow up the safe with acid or melt the hinges with lye, we eventually get the thorium into a liquid solution. But we're still left with a chemical soup. We have liquid thorium, liquid uranium, rare earth elements, iron, and a bunch of junk metals all swirling together. How do we fish out just the thorium?
This is where we cross into the cutting edge of chemical separation. The traditional workhorse of the industry is solvent extraction. You take your acidic water soup and you mix it with a specific organic chemical and extractant that is dissolved in a solvent like kerosene.
Because oil and water don't mix.
Right. You vigorously mix the two liquids in a tank. The extractant is chemically engineered to have functional groups that bond exclusively with the thorium ions. It ignores the iron, ignores the rare earths, and grabs the thorium.
And then?
The organic solvent physically pulls the thorium out of the water phase and into the oil phase. You let the tank settle, the oil floats to the top, and you skim the thorium-loaded oil away.
Our sources mention organophosphorus reagents as the old, reliable tools for this, things like TBP or tributyl phosphate.
TBP is the classic, but it has a massive limitation. It only works efficiently if the water phase is highly, highly acidic. If you want to use a less aggressive acid to save on costs and environmental impact, you have to use a different extractant, like D2EHPA.
But the MDPI review notes that D2EHPA has a serious physical flaw when used at scale. It is prone to forming what chemists call a third phase. What does that actually look like in an industrial plant?
Imagine shaking up a bottle of oil and vinegar for a salad dressing. Normally, it separates back into two clean layers, but occasionally a thick, gummy emulsion forms right in the middle. In solvent extraction, this third phase is a viscous, useless sludge.
Oh, gross.
It traps the thorium, clogs up the intricate piping of the mixer-settler tanks, and ruins the continuous flow of the factory.
Which is exactly why the industry is desperate for next-gen extractants. The review highlights diglycolamides, or DGAs. These complex organic molecules offer much higher selectivity for thorium without the volatility or the messy third-phase issues of the older phosphorus-based chemicals.
But DGAs and TBP are still fundamentally bulk liquid chemical processes. They require thousands of gallons of toxic, flammable kerosene. The true horizon of this field is moving towards solid-state extraction, specifically using highly engineered materials like MOFs and IOPs.
Let's explore MOFs first. Metal organic frameworks.
MOFs are incredible feats of nanotechnology. They are highly porous, crystalline materials made of metal ions connected by organic ligands. They essentially look like microscopic scaffolding. Okay.
Because we can engineer the length of the ligands, we can precisely control the size of the pores in the scaffolding. You engineer a MOF with pores that are exactly the right size, shape, and internal charge to trap a thorium ion, and absolutely nothing else. You drop the solid MOF powder into the liquid soup, it acts like a highly targeted sponge absorbing only the thorium, and then you just filter it out.
Wow. But my absolute favorite technique detailed in the paper is ion-imprinted polymers, or IIPs. This is mind-blowing chemistry. It's essentially the molecular equivalent of casting a mold of a key.
The precision of IIPs is astonishing. Let's walk through how they are made. You start by taking a target ion, in this case thorium. You mix it in a solution with specific organic monomers that have an affinity for thorium. Those monomers cluster around the thorium ion, forming chemical bonds.
Right.
Then you introduce a cross-linking agent and apply heat or UV light to trigger polymerization.
So you're basically freezing the monomers in place, building a rigid synthetic plastic shell around the thorium ion. Exactly. Once the polymer matrix is solid, you wash it with a harsh aluminum, a chemical that breaks the bonds holding the thorium but leaves the rigid polymer intact. The thorium washes away, leaving behind an empty cavity inside the polymer.
And that cavity is a perfect microscopic lock. It possesses the exact geometric shape and the exact electronic charge distribution of a thorium ion. You can take that highly specialized polymer powder, dump it into a chaotic soup of rare earths, iron, and uranium, and it will ignore all of them. It only snaps up the thorium ions that perfectly fit the lock. It is the ultimate expression of chemical selectivity.
It is brilliant, but we have to mention the technique that is truly pushing the boundaries of what is possible: electrosorption.
Using electricity instead of chemical solvents to pull the metal out.
Exactly. The reliance on liquid solvents and massive amounts of acid is the Achilles heel of the entire industry. Electrosorption attempts to solve this by using advanced, highly conductive carbon-based electrodes. The paper highlights an incredible futuristic material called MOS2 at RGO aerogels.
That sounds like something you'd use to build a warp drive.
It practically is. It stands for molybdenum disulfide, anchored on reduced graphene oxide. It is a highly porous 3D aerogel structure. The graphene provides a massive surface area and incredible electrical conductivity, while the molybdenum disulfide provides specific active sites that thorium ions are drawn to.
So how does the extraction actually happen? Do you just plug it in?
Pretty much. You place these aerogel electrodes directly into the liquid waste soup and apply a specific electric potential voltage. The electric field physically pulls the positively charged thorium ions out of the liquid and absorbs them directly onto the surface of the graphene aerogel through a combination of electrostatic attraction and chemical bonding.
No acids, no flammable kerosene, no gummy third-phase sludge, just pure voltage.
And when the electrode is completely saturated with thorium, you remove it, place it in a clean recovery tank, and simply reverse the voltage. The polarity flips, the electrode repels the thorium, and it drops off into a pure, concentrated solution.
That's amazing.
The capacity numbers are staggering. These aerogels are hitting absorption capacities of nearly 4,000 milligrams of thorium per gram of material. It is remarkably efficient, clean, and the electrodes can be reused over and over again.
That is an incredible technological leap.
Yeah.
But we have to address the massive glowing elephant in the room. All this chemical wizardry, whether it is blowing up the safe with acid, casting polymer locks, or using graphene aerogels, it leaves behind a very real, very dangerous byproduct. we are dealing with radioactive materials.
Yes, we cannot gloss over the radioactive reality and environmental safety of this process. Managing the waste is the single biggest hurdle to a thorium future, and honestly the bottleneck for rare earth independence. When you process monazite ore, you generate massive amounts of solid wastes. The industry refers to these primarily as water leach purification residue, or WLP, and neutralization underflow, NUF.
And we need to be clear, these aren't just muddy rocks. They contain concentrated levels of dangerous, highly radioactive isotopes. We're talking about actinium, residual uranium, radium, and heavy toxic metals like lead. If this material is stored improperly and leaches into the groundwater, it is a localized catastrophe.
Which is why the sources emphatically stress the absolute necessity of multi-barrier storage systems.
Right.
We can no longer rely on simple earthen tailings ponds that can breach during a heavy storm. The industry is actively moving toward advanced immobilization techniques. The most prominent are cementation, mixing the waste with specialized concrete, and more importantly, vitrification.
Vitrification meaning turning the radioactive waste into glass.
Exactly. You take the highly radioactive residue, mix it with silica and other glass-forming chemicals, and melt it down at incredibly high temperatures. When it cools, the radioactive isotopes are completely locked inside the amorphous molecular structure of the glass block.
The advantages of glass are obvious. Glass doesn't rust, it doesn't dissolve easily in water, it doesn't break down chemically over time, it isolates the radiation from the biosphere for the thousands of years it takes for the isotopes to naturally decay to safe background levels.
But even with vitrification and multi-barrier systems, public opposition to any processing facility involving radiation is a massive, incredibly complex hurdle. People hear the phrase radioactive waste and they want it absolutely nowhere near their towns, their water tables, or their state lines.
And given the mining industry's historical track record with environmental safety, that skepticism is entirely justified.
If we connect this to the bigger picture, the entire future of the thorium fuel cycle, and honestly, the entire domestic rare earth supply chain itself, depends entirely on whether the industry can manage this waste transparently and safely. The industry must move toward closed-loop water cycles, where zero toxic liquid ever leaves the plant boundary. They must implement low-waste technologies like the electrosorption we just discussed, which drastically reduces the sheer volume of chemical reagents used. Because ultimately, without public trust, the science doesn't matter. You cannot build the clean energy infrastructure of the future if the public fundamentally believes the manufacturing process is poisoning their backyard.
So what does this all mean for you? We have traced a singular, unbroken chemical thread across 2.4 billion years of Earth's history. We started with microscopic cyanobacteria exhaling the very first breaths of oxygen, overwhelming the Earth's iron and methane sponges, forcing an evolutionary leap and plunging the planet into a global ice age.
We saw how that surge of oxygen was permanently recorded in the indestructible lattice of zircon crystals, creating the Cerium anomaly, a chemical diary entry proving the atmosphere had changed forever.
We looked at Cerium's siblings, the 17 rare earth elements. We explored how their deeply shielded electrons give them unparalleled magnetic and optical properties. And we realized that the screen you are looking at, the energy grid you rely on, and the global communication networks you use are completely tethered to these heavily dispersed, incredibly hard-to-mine elements.
And we ended at the incredibly complex, highly promising threshold of thorium, a radioactive hitchhiker hiding in rare earth mines. We saw that if we can overcome the brutal chemical bottlenecks of extraction using things like ion-imprinted polymers and graphene aerogels, and if we can earn the public's trust regarding waste management through vitrification, thorium could literally power human civilization cleanly and safely for thousands of years.
It is a profound realization that our most advanced future technologies, our MRIs, our wind turbines, our next-generation nuclear reactors, are entirely dependent on exactly how the Earth's crust cooled and oxidized billions of years ago. But before we go, I want to pose one final thought. We have spent this entire deep dive talking about extraction, digging up the rock, breaking the chemical bonds, separating the elements. What happens when we hit the absolute limit of that paradigm?
It raises an incredibly important question, one that builds on everything we've discussed today but pushes us beyond the scope of our current sources. We have spent the entire history of human civilization extracting what the Earth naturally created, from smelting early iron to crushing monazite for rare earths and thorium. But as we run into the physical limits of extraction, the harsh limits of chemical toxicity, and the hard realities of geopolitical borders, will the immense difficulty of mining these F-block elements finally force humanity to stop digging? Will the sheer cost of solvent extraction force us to synthesize artificial supermaterials? I am talking about metamaterials engineered atom by atom at the quantum level that perfectly mimic the magnetic and catalytic properties of rare earths, completely bypassing our reliance on the periodic table's natural offerings.
That is a staggering concept,
Yeah.
moving from being miners of the Earth's past to architects of our own atomic future. We might finally put down the muddy, water-stained chemical diary and start writing our own pristine textbook from scratch. Thank you for joining us on this deep dive. Keep questioning the world around you, keep looking beneath the surface, and we will see you next time.